my previous video, I had defined uniform convergence of a sequence of function and pointwise convergence of sequence of function. Today I will discuss this part also elaborately because this topic is very important for any competitive exam. But at first I will highly recommend you, if you don't see my earlier video, please see my earlier video at first. First, just recall the definition of uniform convergence. Fn be the sequence of function which is defined from x to r, and f be any function which is also defined from x to r. Then Fn converges to f uniformly if for all epsilon greater than 0 there exists an capital N which depends on epsilon. This is the actual difference uniform convergence to pointwise convergence. Because in pointwise convergence, capital N depends on epsilon and as well as points. But in uniform convergence, capital N depends only epsilon, such that absolute value of fnx minus fx less than epsilon, and this is true for all n greater than equal to capital N and for all x belongs to x. But fn does not converges to f uniformly means there exists epsilon greater than 0 and there exists nk and xn of the points in the set x such that absolute value of fnk xk minus f of xk greater than equal to epsilon. Here notice, not for all epsilon. If we can to find at least one epsilon and one point such that this break this relation of uniform convergence, then this would be not uniform convergent. Notice one thing, there exists nk. That means if we can find one subsequence which will break this relation, that means the function is not uniformly convergent. Just recall, this is the same as sequence does not converges to limit, because I have seen in sequence does not convergence means if we can to find one subsequence which does not converges to limit, then we can tell easily the sequence does not converges to the limit. Same as uniformly convergent. Actual picture of uniform convergence means after some stage capital N, all the function fn lies between the epsilon neighborhood of f. This is the picture of uniform convergence we all of us know. Now I will see another method to find the uniform convergence of sequence of function. Two function f and g, where f defined from I to r and g defined from I to r. Suppose this is the f function and this is the g function, and at the point x0 the difference between these two functions would be fx0 minus g of x0. Then the difference between two functions at the point of the domain would be such type. And this would be obviously be number. Now the supremum distance of these two functions would be supremum of distance between fx minus gx, which is actually denoted as supremum distance, which is denoted as norm of f minus g infinity. And for uniform continuity, if norm of f minus g infinity tends to 0 as n tends to infinity, then the sequence is sequence of function B uniform continuous. Okay, this is a nice criteria for uniform convergence. Sequence fn and f be mapping from any interval j to r, then fn converges to f. This convergence be uniformly when if limit n tends to infinity supremum of the set absolute value of fnx minus fx where x belongs to j equal to 0. This is the uniform convergence criteria to find uniform convergency of sequence of function. Okay, so is always trivially because the definition of uniform convergence means we all of us know for all epsilon greater than 0 there exists a capital N belongs to natural number such that for all n greater than equal to capital N and for all x belongs to j, absolute value of fnx minus fx less than equal to epsilon. Therefore, from this line, it is true for all epsilon greater than 0, there exists capital N which belongs to natural number such that for all greater than equal to capital N, the set supremum x belongs to j such that fnx minus absolute value of fnx minus fx, this set be the less than epsilon. This condition actually trivial condition. That means from this line, if we consider this supremum as mn, from this expression obviously mn tends to 0. Are you getting? Well, now I will study the vector space, metric space, norm. Then extension of this theorem is such type: if capital A is any subset of R and phi be a mapping from A to R, which is a function, say set if phi is bounded on the set capital A, then define the uniform norm of phi on the set A by the norm is defined as norm of the set phi x where x belongs to A. This is the norm. I will see later what is the norm actually in vector space, metric space. Just think, this is the set and this set is bounded and supremum of this set is defined as the norm A. Now, a sequence of function fn or which be bounded function on the set A, that means all sequence of function here bounded. Then we can tell this sequence of function converges on the set A if norm of fn minus f tends to 0. Are you getting? Well, as for example, consider a sequence of function fn which is defined from closed interval 0, 5 to r such that fnx equal to x square over n. Here the set A equal to closed interval 0, 5, then we have to prove fn converges to 0 uniformly on the set A. Since here the function is defined from closed and bounded set to R, since this function is polynomial function, so always continuous, so obviously this function would be bounded because here the domain is closed and bounded. That means here the given function, sequence of function fn is bounded on the domain close 0, 5. Okay, and this is true for all n belongs to natural number. Now, what is the f? I had seen in my earlier video about this function. I have seen fnx converges to 0 pointwise. That means here the f function is 0 function. Okay, so we have to prove the function is uniformly convergent. That means we have to prove supremum x belongs to A, fnx minus fx tends to 0. Okay, that means this would be supremum x belongs to A, fnx means x square over n minus 0, and here supremum x belongs to A means closed 0, 5, and this is the absolute value of x square over n, and in the interval 0, 5 this supremum would be 25 over n. Then now we have to find this limit tends to 0 for uniform convergent. That means we have to find limit x belongs to, here the A is 0, 5, the set fnx minus fx, this absolute value tends to 0 as n tends to infinity, and obviously this value equal to 25 over n. Then as n tends to infinity, this value tends to 0. So our proof has done. This sequence of function converges uniformly on the set A. Are you getting the method? We will see another function fn defined from closed interval 0, 1 to r, and the sequence of function is look like fn x equal to x to the power n times 1 minus x. From this line we can write it as easily x to the power n minus x to the power n plus 1. Notice the graph of the function. This would be f1 x times 1 minus x. This would be f2 x squared times 1 minus x. This would be f3 x cube over 1 minus x. And this is f10, f20. Are you getting the picture of the function? Well, at first, for uniform continuity, we have to check at first the pointwise converges. Here, obviously fn0 equal to 0 and fn1 equal to 0. And since xn lies between the interval 0 to 1, then absolute value of x to the power n times 1 minus x, obviously this value less than x to the power n, and in the interval 0, 1, since x to the power n tends to 0, so obviously this function in the interval also tends to 0. That means our given function x to the power n times 1 minus x is pointwise converges to 0 function. That means here this function converges pointwise to fx equal to 0 function. Okay. Now we have to find is this function is uniform convergent? For this, we have to check supremum x belongs to closed interval 0, 1, absolute value of fnx minus fx tends to 0 function. Put the value. This value would be supremum x belongs to closed interval 0, 1, x to the power n times 1 minus x. We have to check supremum of this function tends to 0 function. For this, at first consider the function gx equal to x to the power n times 1 minus x. And to find the maximum of this function, we all of us know we have to find such point such that g prime x equal to 0. And if you calculate the g prime x, then this would be this type, and the point in which the function g prime x is vanishes, the point would be n over n plus 1. That means fnx has a maximum at the point n over n plus 1. This is obviously less than equal to 1 over n plus 1. So, obviously, supremum x belongs to closed interval 0, 1, absolute value of xn times 1 minus x. This value obviously less than equal to 1 over n plus 1. And then, since this value obviously tends to 0, that means obviously limit of this supremum tends to 0. Means our given function be uniform continuous function. Are you getting? Well, next function is fnx equal to nx over 1 plus nx, which is defined for all x belongs to closed 1 open infinity. And notice the graph is look like this is the f1x, this would be the f2x. The graph would be such type because the f1x would be x plus 1 over x, f2x would be 2x over 1 plus 2x, so on. Are you getting? At first, to find the uniform continuity, we have to find what is the pointwise convergent of this function. fnx equal to nx over 1 plus nx. Then, limit n tends to infinity, fnx would be x over 1 over n plus x. Then this value would be 1. That means actually this sequence of function, all the sequence, if this is the 0, 1 interval, all the sequence the converges to 1. Are you getting? And this convergence is actually the pointwise convergence. Now we have to prove, is this convergence is uniform convergence? Here I will apply the supremum method. That means norm of fn minus f infinity, which is equal to supremum x belongs to closed 1 open infinity, absolute value of fnx minus fx. Now we can apply this method because here the sequence of function fnx is bounded function for all n belongs to natural number, and also the function fx is bounded. So we can apply this theory. Just notice here the fx function and each fn, all fn here bounded. Therefore, and this value would be, just put the value, this is would be supremum x belongs to close to 1 open infinity, fnx means nx over 1 plus nx minus 1. Then this is equal to supremum x belongs to closed 1 open infinity 1 over n plus nx. Since the function is monotone decreasing function, so obviously supremum exists at the point 1. That means this value would be, if we put the value, this value would be 1 over 1 plus n. And as limit n tends to infinity, obviously this limit tends to 0. That means our given function is uniform continuous function because this limit tends to 0 as n tends to infinity. Means this convergence, not only pointwise convergence, this function converges to fx equal to 1 uniformly. Are you getting clearly what is the uniform convergence in sequence of function? How we have to find? Well, consider one interesting example. Same sequence of function, that means fnx equal to nx over 1 plus nx, but here the domain has changed. That means here the domain not 1 infinity, just here change, here also in the domain the 0 value has included. Now the question is fn is pointwise or uniformly convergent on the interval close 0 open infinity? Notice fnx equal to nx over 1 plus nx, where x defined from close 0 open infinity, which is defined for all n belongs to natural number. And notice pointwise convergent means first we have to find the limit. Notice here one thing, here f0 equal to 0, and also similar to before, limit n tends to infinity, fnx equal to x over 1 over n plus x, this is equal to 1. That means this value is true for all x belongs to close to 1 open infinity. That means since here the value 0 has included in the domain, that means this sequence of functions convergence pointwise to the function fx equal to 0 when x equal to 0, otherwise 1 when x belongs not equal to 0. That means x belongs to close to 1 open infinity. To find the uniform continuity, since here fx is two different type, when x equal to 0, then fx is 0, then the value would be supremum x belongs to close to 0 open infinity nx over 1 plus nx. And obviously this supremum is 0 always, and otherwise fx equal to 1, then this value would be supremum x belongs to close 0 open infinity fnx minus fx. If we put the value, this value would be supremum x belongs to close 0 open infinity 1 over 1 plus nx. And similar to before, since the function is monotone decreasing function, so obviously the maximum value exists at the point 0. And notice here at the point 0, the supremum value is 1. And since I have got the supremum value is 1, That means our condition has broken here. Function is not uniform convergent when the domain defined close 0 open infinity. There exists a nice theorem. If fn be sequence of continuous function which is defined from x to r, where n belongs to any natural number and x be any subset of r, then fn converges to f uniformly. That implies the limit function f, which is defined from x to r, is obviously continuous function. So, to find the uniform continuity, this is the shortcut method. If you can to find points not be convergent to continuous function, then the sequence not be uniform continuous. And you had noticed in this sequence, the sequence of function converges to pointwise this function, and this function not continuous at the point 0. So, we can tell easily the function not be uniform continuous. When the function converges to uniformly, then obviously the function converges to always the continuous function.